Hello, everyone. It's my pleasure to introduce Jemma Issroff. Jemma is a Ruby core committer, and she works at Shopify as a senior developer on the Ruby infrastructure team, and I have to tell you, it's been a pleasure working with her. She's also a co-founder of WNB.RB, women non-binary Ruby community. You can applaud. And she's also a co-host on the Ruby on Rails podcast. Please give her a warm welcome for presenting her talk titled Popping into CRuby.
Thank you, Ufuk. Good morning, everyone. So a little while ago, I was looking at a file within CRuby's codebase at rubycompile.c. And as the name suggests, it's where most of the compiler code lives. Now, if that's not familiar to you, my goal today is that by the end of the talk, you'll understand what I mean exactly by that. And so I was looking specifically at this method, this icompileEach method. And something caught my eye as a little abnormal or something that I didn't right away know what it was or what it meant. And it was this popped parameter. And popped was sprinkled all throughout this method. It was a huge method with popped in various different places like this. And I found it actually, as I learned more about what popped was and specifically what its functionality was, I found it interesting enough that I thought and hoped you all would find it the same. So today we're going to talk about popping into CRuby. If we haven't met yet, I'm Jemma. I use she, her pronouns. I would love to meet you. Please come say hello at any point during the rest of the conference. As Ufuk, my manager, just mentioned, I work at Shopify on the Ruby infrastructure team. And I'm also the co-founder of WNB.RB, which is a women and non-binary Ruby community. We're actually having a little dinner tonight. If you're a woman or a non-binary person, please come join us. It'll be at Cafe Coyote from 6 to 8 p.m. You can find more info in the Slack if you'd like to join. OK, so we can think of our Ruby programs or applications that use Ruby as some car. We've seen metaphors like this perhaps in the past. And like most car metaphors, we might not have thought much about what goes on under the hood. And the smoke here is not because there's anything broken under the hood, per se, just because there's some really interesting stuff happening under the hood that we might not have really thought about with our Ruby programs. Right, we know our Ruby code is somewhere in there. There's also some bytecode going on somewhere in there. There's parse trees going on somewhere in there. And today we're going to talk about all three of these things and how they relate, and specifically how they relate to this concept of popping. So we start with our Ruby programs, and when we run our Ruby code, the first step is they go through this parser. And they become what's called an abstract syntax tree, which is a representation of our programs in a tree form. So what does that practically mean, right? How can we represent our programs in a tree form? Well, let's look at an example here. So if we have a very simple class conference, it has one method name in it. We'll look through and see kind of at a high level, blurring some details, but what the nodes are and what the structure of this tree will become. And you can actually see this for any Ruby file you have. You can pass a parse tree to this --dump parameter. So ruby --dump equals parse tree, and pass in the name of your file. And you'll see the entire parse tree for any Ruby code you have. But kind of looking at a higher level again, if we have this conference class, the first kind of node we'll get is, as we might expect, a class node, which is going to have a few children. Nodes can have many children, depending on the type of node. They also have things like locations, for instance. And so a class node has a few children. In this case, one of them is the name. This name conference is a child node. Ruby calls this a colon node. And another child, as you might expect, is this method, right? A definition node, it's called, which encapsulates a whole method itself. And within that method, within that definition node, we also have quite a few child nodes here. So for instance, one we have that's a little invisible to us in this case is an args node, which is going to contain all the arguments for a method. Another one we have here is this string node, which is actually itself encapsulated within a body node, but we're going to blur that a little here. And so we have another child that's this RubyConf string. And this is at a high level the parse tree we would get for a program that looked something like this. What's important to note about this abstract syntax tree or parse tree is that it represents all of the code, right? Every line of code, every little piece of code we've written needs to be in this tree. And you might think, why, right? Why can't we optimize out parts of the code even at this first step and just simplify a little bit to maybe make the parse tree smaller or faster, anything like that? And it's because running the code isn't the only thing that happens to this parse tree, right? There are other consumers of the parse tree. And their goal isn't necessarily a successfully running program, but it's to use the AST to do something for similar purposes. So yesterday there was a Hack Days project to do with the LSP, which is an example of something that would require a parse tree or a linter or RuboCop or anything like that. Which would all critically need the full tree. You might have heard also about Prism, which is a new Ruby parser. It was at one stage of its life called YARP. You might recognize it by that name. You might have seen it. My colleague Kevin Newton gave a talk about it at RubyConf. He's written about it. I've done some stuff with it, created some bugs about it. It's been in Ruby Weekly. Just last week, Kevin won the Ruby Prize for his work on this, which deserves an applause, certainly. Yeah, and this is all Prism, but you might have heard about it and not be entirely sure what it is or what its goal is. It actually also creates an abstract syntax tree. But it's a little different. Its tree has the same information. Again, we just went over why it's important that it should contain all of the information, but it's represented slightly differently. I'm not going to walk through too many examples of differences, but just if we look again at our previous snippet, this args node, as we mentioned, was empty, right? So it's not actually adding information to have an empty args node. Prism instead has nothing there at all. And there's a little bit of, in my opinion, clearer naming around Prism nodes. So for instance, instead of a colon node here for the conference name, you have a constant read node. And those are just some examples of how Prism's AST are different. You might be seeing this and think, well, why create a new Ruby parser? The old one is clearly working, right? All of our Ruby programs are running. What's motivation here? This is a slide from Kevin's RubyConf talk. I'm not going to go through each of these, but I just want to talk about the first point he made to motivate Prism, which is error tolerance. And the key here is this word tolerance, right? That the parser can actually recover from errors and still keep parsing. So if we look at this class syntax errors, I'm going to take a sip of water and give you a few seconds to try to figure out how many syntax errors there are in this class. I heard a 2. 3. All right. Yeah, there are certainly 3. So as you might have found, there's 1. There's nothing after this ampersand, ampersand, which is 1 syntax error. There's a missing end closing out this class. And also these parameters are in the wrong order. The optional parameters need to follow the required parameters. And if you run this through Ruby's existing parser, you can actually just check for syntax by running ruby-c. You get this back. unexpected local variable or method, syntax error, and it's pointing to the B. Now, if you know what's going on, that's perhaps very clear to you. I think especially if you're a beginner Ruby programmer, this error message isn't making it very obvious what's unexpected about this, right? Like, why is this wrong? What's going on here? It's talking, of course, about the B being in the wrong order, right? As we just discussed, it needs to be earlier. And it also gives us this unexpected end, which is also a little confusing to me. Right? What it's saying here is this end is unexpected because it wanted something else to follow the ampersand. But instead of saying, hey, there's nothing following the ampersand, it's just telling us the end is unexpected. And it notably doesn't mention this missing end, the third syntax error we just discussed. If we look at Prism instead, you can run it right within there are many ways to access Prism's parser. One of them is to run right within Prism directory. You'll get these parse errors. I've changed the formatting slightly. First, you'll get unexpected parameter order, which is exactly what we discussed and what we want here. Second, you'll get expected an expression after the operator. It's not only pointing you to the right location in this error message, but it's telling you explicitly what it was looking for that wasn't there. You'll get that it can't parse the expression overall. And you'll also get expected an end to close the class statement, which is explicitly, it's not only telling you that you were missing an end, but it's also telling you which thing the end should have corresponded to, the class statement. So Prism already exists as a gem. You're welcome to use. Many projects have already started integrating with it. It's also hopefully going to be included as part of Ruby 3.3. OK, so we went over our parsing step, right? Our code starts, it goes through the parser, it becomes this syntax tree. What happens next? The next thing it becomes is bytecode, and it does that by running through the compiler. Prism, as we know, has its own parse tree, right? So this existing compiler isn't going to work in its entirety for Prism because it's expecting different node types. So the work I've been engaged on for the last few months is working on a compiler for Prism, which actually needs to generate the same or at least very similar bytecode so that the virtual machine, which we'll discuss in a moment, can take that bytecode and execute the program. And we've done a lot of work so far on this compiler for Prism. There's still a little left to go before the next Ruby release on Christmas. OK, so let's look at how the compiler works. So we have, as we've just discussed, our parse tree, our AST here. And what happens with the compiler? Well, we know earlier we were talking about this IC compile each, which is actually the crux of what the compiler is doing. This switch statement in C is very similar to a case statement we might be more familiar with in Ruby. And it's going through all of the node types and recursively compiling them down. And we can actually see the results of the compiler, see the bytecode it dumps out by passing in insns to dump. So we can do that with our little Ruby file, conference.rb, and we'll get out some instruction sequences, which might look a little vague. I wanted to call out this first one here you might have seen is like put nil, right? What does that even mean? Put nil where? What are we doing? What is it? What is happening? Why is it relevant? Yeah, and so we'll get into that in a moment. But so our virtual machine is what's really critical to understand here. And the virtual machine is called YARV, which stands for Yet Another Ruby Virtual Machine. That's why Prism was initially YARP, Yet Another Ruby Parser. But its name has since changed. YARV is a stack-based virtual machine. So what does that mean? In order to understand stack-based and what that means, we're going to run an even simpler program. We can pass with -e our entire program here, which is just going to be 2 plus 3. So adding 2 numbers as our Ruby program. And we'll get 4 instructions out of that. These puts, what they're saying is put something on the stack, right? So put object is saying, hey, put an object on the stack for the VM to use. So we have a put object 2, we're going to put a 2 on the stack. Then we get a put object 3, we're going to put a 3 on the stack. The next thing we get is this plus operation. The plus operation has a receiver, and in order to get the receiver, it's going to pop the first value off the stack. So 3 is going to be the receiver for this plus method. And then plus is going to be called, we can see here, with 1 argument. So plus needs 1 more argument, which we'll also get by popping the value off the stack. And you might have heard me overemphasize the word pop right here, right? We're putting things onto the stack, and then we're popping them off, which we'll get into why that's relevant, why I named the talk this. But so in our conference instructions, we see this put nil, right, which is putting a nil value onto the stack. We see put object name, which is putting at some point this symbol name onto the stack. We can see other things like put a string onto the stack. And this is, I don't want to go through every instruction here, but at a high level, this is what's happening with our instructions. And we can kind of see where they map here, right? So block by block, we can see this first block is our class block, right? We can see the define class conference within that block. This second block here we can see is defining the methods within our class conference, right? We can see it has this define method, it's putting the name object. And the third block within here is the contents of the method itself, which is this put string RubyConf. And I want to actually zoom way into the method to understand popped and what's going on, and why it's potentially interesting or why I think it's important to us. Okay, so to start off with, let's assume we have a new Ruby program. This is our entire Ruby program. If we run it through the parser, we're going to get, actually, there's a node I ignored earlier, which is a scope node. And it's an overall node that surrounds things like methods or blocks or things like that, puts them into a scope. So we'll get a scope node, and within that scope node, we'll just have a string node. And as soon as we run that through the compiler, we'll go into this IC compile each method eventually. And the case I highlighted here is node lit. But node string, string node, works pretty similarly. The only difference is instead of a put object, which happens on the literal nodes, we get a put string. So sure enough, if we run this through the compiler, we'll get a put string RubyConf, and then we'll get a leave, which just pops the value off the stack. So we'll put the RubyConf onto the stack, and we'll pop it off the stack, and that's what our program will return. Now, when we were talking earlier about the parser and the abstract syntax tree, we said it had to be thorough, and it had to contain all of the information. Notably, it couldn't have any optimizations, because there were other consumers. This isn't true of the compiler. This compiler step is actually a compiler step with optimizations. And there have been several talks in the past, I think probably more than I can count, about different optimizations within compilers. Just to highlight a few, Maple Ong last year at Uruko talked about looking into peephole optimizations. There's a huge amount of work around YJIT and talks and blog posts and articles. You can learn other things that are interesting happening within the compiler. John Hawthorne gave a talk at RubyConf Mini last year about making ISA fast, which goes into several parts of this as well. But the one I want to talk about today is this popped optimization and what it means. And in order to understand that, we're going to make our program just slightly more complicated. We're going to add an integer to the end. So it's now our program is a 2-line program. The first line is this string RubyConf, and the second line is this integer 2023. And if we run it through the parser, as you might expect, we now have another node to represent that 2023 number. It's a literal node, which represents the integer. And as it goes through the compiler, this is actually the instructions. These are the instructions we get. We just get a put object 2023 and then a leave, which I hope is making you ask the question, what happened to the put string, right? Where did that go? Why is it all of a sudden not there when it was just there when the program was only a string? And so what you might be thinking here, imagining would have happened is, well, we had this program, RubyConf, and then the number 2023. We just went over how RubyConf is going to put a string RubyConf onto the stack. 2023 is going to put an object 2023 onto the stack. And then leave is going to pop that 2023 off the stack and return it. But what you can see here is we have something left over on the stack, right? This RubyConf, no one ever touched it. It was unnecessary. It was taking up space on the stack, which maybe isn't relevant in this tiny example, but you could imagine is relevant in a bigger example. And it was also just unnecessary work to put the string, which again, in this tiny example, not super relevant, but in a big example where you really want your code to go fast, why are we putting this string that we're never going to use? And that is exactly the popped optimization, right? It's that if we're not thinking about it, if it's not in our little imaginary thought bubble, what's happening here is the RubyConf that we're never going to use, that string that is irrelevant, just gets popped right away, and it never even becomes an instruction part of the instruction sequence. Instead, we just have put object 2023, which puts this value 2023 on the stack, and the leave, which pops 2023 off the stack and returns it, and then our stack is empty, right? We're not adding any extra information there at all. And we can actually see that in this method we have, right? We have this if not popped, which has been passed down, right? Only add the put string if it's not popped. And I want to talk about a few other examples of popping in Ruby and what can't be popped. So things that can't be popped. If our entire program was just a string, we need to return that string, right? The program is going to return that value, and so that value cannot be popped. Or if we had a method definition, the method now is going to need to return that value, right? So even though it's a string, it still can't be popped in this case. Or if we were assigning it to some local variable, in that case, we also couldn't pop the string because the variable is going to need the value of the string. Or if we had some method call, right? We also, in this case, couldn't pop the string because the method call, if we popped it, then the method call would not have the arguments that it needs. Now let's look at and think through some examples of things that can be popped. So in order to show examples of things that can be popped, we want to put something for the program to return at the bottom so that it's not just assuming it's returning everything. So we're putting this string RubyConf at the bottom. But we know strings can be popped, right? We just looked at that example. Strings can be popped. Other literals like symbols can be popped, or numbers can be popped. Or even arrays with literal values, right? Like this array, nil, true, false, can all get popped. And what's interesting here is there's some nesting going on, right? So like a hash with just symbols and numbers and arrays in here can all be popped because none of this has side effects, right? There are no things later on that are expecting any of these values if this is just a line on its own. And sure enough, if we dump the instruction sequences for this, we'll just get a single put string RubyConf out of all this code and then a leave. Right? Nothing's happening in terms of generating instruction sequences for anything else in the program. But I want to dig in a little more into this nesting and what's going on here. Specifically, this concept of popped and this integer popped or Boolean popped, which it could be, gets passed down recursively through the tree as we're generating instruction sequences. And so as we're generating instruction sequences for this hash, what's happening is the hash is saying, hey, generate instruction sequences for the array, which is a child, and pass down this popped, whether or not we're getting popped overall. And there are some things that'll ignore that value of popped, right? Like say within this we had another hash, and within that we had another array, and within that we had a method call. Well, we know from earlier we can't pop that string because we need that value. So something like a method call is going to ignore the popped value when it's compiling its arguments. Which means that can't be popped, right? This example can't be popped. And we've had several examples of things that cannot be popped, and several examples, too, of values or things that can be popped. So I hope that gave a pretty good overview of popping into CRuby, of what this concept of popped means. And when working on this talk, I was thinking about popping as a concept and thinking about what types of work we do and don't pop, right? And thinking about how usually many of us don't actually think of this, don't actually think about what's going on with Ruby and what's happening behind the scenes. And in a way, we've popped this concept out of relevance for ourselves. But all of this is happening behind the scenes and is actually really making our programs faster and more efficient. And I think, to me, for that reason, is worth learning about and potentially even working on. Hack Days was yesterday. Otherwise, I would suggest it as a really good outlet to work on things like this. But there are still you can get in touch with many folks here who ran different Hack Days or are running different projects or giving different talks. If you're interested about how you might learn more about these concepts or dig in more to more deeply understand them. And I actually tried to sprinkle throughout the talk a few different resources you can look into to learn more if you're interested. Or you can Google any of these concepts or anything like that. But my hope is that you really continue to engage with concepts like this. Thank you so much.